Recording is rolling on Thursday, September 23rd. Yesterday, I had guys in the lab doing this half of this Atwood lab, the classic double elevator. Today, I'll have you guys doing this modified Atwood version. So, some things about class. Remind you guys that this homework is due tomorrow, which you guys probably already have finished since I covered these problems in class. If you want to do the bonus homework and get even more points, then that opportunity is still on the table. I want to give you guys some tips about how this lab's going to work out. Actually, I want to give you guys the answers. Go ahead and do that at the start of class here. So the question for each one of these parts, and of course you guys did this half yesterday, was what is the acceleration of the system? Let's say each of these blocks can have some magnitude of acceleration. One was going down, one was going up, and then today one's going to go down, one's going to go to the side. But there's some magnitude of that acceleration. Can you find out what that is? There are two approaches that we can do in class. One is that we can solve this on paper with Newton's second law of motion through a free body diagram. And the other way is that you guys can go back to the lab area and gather some data empirically, right? And then calculate the acceleration and see if you can figure out what is that acceleration as a function of the masses. Remember, the answer at the end is just in terms of variables, like just in terms of the answer of masses. But like I mentioned too, I want to take you guys through the paper version of that. So what's that? Yesterday, we made both of these before I sent you guys back to the lab area. The free body diagrams for the double elevator Atwood, which you guys did yesterday, and also the modified version that's going to have one vertical, one horizontal, that you guys are going to get some data for today. Let's go through and figure out what would the acceleration be for each one of those Atwood setups. Let me do this way. Let's divvy this paper in half, and then we'll do double elevator on the left side. So double elevator Atwood versus single elevator Atwood, like the modified version. Okay. So these would correspond to these diagrams. Now, if you want to know what is the acceleration, and that's the whole question in this lab, what's the acceleration of the system? Acceleration of the system. You could go through Newton's second law of motion, which is the approach we're doing right here. Net force acting on total mass. No, of course, this was true for both of these. The acceleration of the system is net force on total mass. And then if you refer back to the free body diagrams that we made yesterday, you could figure out what the net force is, and then you can actually get the answer really quickly from that. So let's start with this double elevator that you guys did yesterday. I see a bunch of different forces. There's the weight of this block pulling down, the weight of this one. There's the tension forces holding them together. We talked about all this yesterday. Which forces are going to feed into this formula? Which ones? I'm thinking the two weights, because wouldn't these be like fighting each other, kind of like a tug of war? But the tensions I'm going to not include in this formula because remember, tension is just internal to the system. It's just holding everything together. It's not driving it to move. Well, it's just holding blocks together. So it's not an external force. So the acceleration of the system, by system I mean, well, this block down and this block up, is equal to, instead of a fraction, now the net force would be, looks like this weight minus this weight. So MAG minus MBG, the difference of those two weights. Pause there just to make sure that makes sense, like why that would be. Remember, we also talked about some boundary conditions you could have here. So at one extreme, you could make these weights the same. And if you did that, what would the acceleration of the system be? If they're the same weight? Yeah, zero. It would just zero out and just kind of hang there. Isn't that consistent with this? Because there would be zero net force. They would just trap. The other extreme is, of course, you could put all the weight on one side, and then it should be that free fall, perfect free fall. And what's the total inertia being moved around? Well, both of the blocks, they each have inertia. So you just add the blocks together, add their masses. That's the total inertia that has to be moved by that net force. That could be the answer right there. I'll do one more thing, just clean this up a bit. I can factor out the free fall rate. And if you do that, then it looks like this. Difference of the masses over sum of the masses all times the free fall rate. Okay. So now you can put in whatever two masses you want. And for that matter, you could even change planets. If you want to say, I wonder how this would work on Mars. If you do Martian graphic, there you go. That is the answer to yesterday's question. What is this box down here? What's the acceleration of the system? Yeah. All right, let's and then of course you guys can look at your empirical data from yesterday and say, I wonder how close that is. Okay. How about for today's? Now today's looks like this. We knocked up this free body diagram yesterday. So you guys see in the lab area that it's going to be very similar to what you did yesterday, except that, well, one of these is moving horizontally. And, there's going to be a Hot Wheels car. You guys get to break up the Hot Wheels cars today. No, guys, that Hot Wheels car, is that part of this mass that's being moved by the net force? Yes, it is. That Hot Wheels car has a little bit of inertia. It's about 30 to 35 grams, somewhere there. They're all a little bit different, but they're about 30 to 35 grams. So make sure that you include that in your mass B, right? Because that's part of the inertia. A couple ways to do that. The sort of quick and dirty way is you can just add 35 grams to the mass. If you want to include the tape, it's probably pretty close to that. But I do have a digital scale and also a classic triple beam balance factor if you want to get your hands on that. But let's go through the same thought process. What's the acceleration of this system? And by that I mean this mass accelerating down and this mass accelerating to the side. Well, what's the net force from all these forces? I got a bunch of forces here. This weight, this tension again, this weight, this normal force. Out of all those forces, what's the net force? Well, I know tension's just internal to the system, like it was on the left side here, so probably just ignore that, right? Just holding everything together. And the weight of the block that's moving horizontally now, this is a new idea, different from yesterday. Isn't this being balanced by the normal force supporting it up? So these two forces cancel out. That means there's only one force left on the board, and that's this one right here. This weight, the weight of the hanging block, is the only force that's driving the system to move. So I'll represent it like that. But how much mass is it moving? The sum of the masses. There you go. The one on the left, that's the answer to the half lab you did yesterday, and this one right here is the answer that you'll get today. Of course, I want you guys to get the data empirically. It's pretty similar setup. The table's a little bit different because setup's a little different. But look at your empirical data once you get it and say, I wonder how close that is. You guys good so far? All right, so I will leave these free body diagrams up here, and I'll walk around, help you guys out. Everything you need is back in the lab area. At the end of the day, just turn your lab into that gray tray. I'll give you some points.